So good afternoon, everyone. First of all, thanks for inviting me here to talk a little bit about the work that we've been doing at Peltarion. So the title of this presentation is Deep Learning Without Big Data, Brain Tumor Segmentation. And I want to start by giving you a little bit of a backdrop on why I picked this title. So at Peltarion, we meet with a lot of external companies that want to build deep learning models. And the question that we get all the time is, how much data do we need? We heard that you need 1 million data points to create a deep learning model. And the CTO of a famous Swedish company once said, we only have 100 million users. Will that be enough to create a deep learning model? So with that in mind, let's jump into the presentation. All right, so my name is Lars Sjösund, and I'm working as a senior AI research engineer at Peltarion. I'm also the chairman of Stockholm AI, the local AI community here. And this work has been a joint collaboration with Jens Sjölund from Elekta. Elekta is a Swedish company that is creating hardware and software for tumor treatment. So brief outline, we'll start by going through a little bit of background to the problem. Then we'll look more at the specific models that we've been using, followed by some results. Then we look at some practical details in training these kind of systems. Finally, we'll look a little bit at some possible future work. But let's start with the problem background. So worldwide, we see around 14 million new cases of cancer each year and almost 9 million deaths. And to make it even more concrete, 2 out of 5 of us here in this room will be diagnosed with cancer at some point during our lives. And here in Sweden, around 50% of people are treated using radiation therapy, where you have a high energy radiation source like gamma rays or X-rays that you shoot at the tumor and thereby killing the tumor cells while sparing surrounding tissue. And this is done in a completely non-invasive way. But to be able to do radiation treatment, you first have to, or doctors first have to create a very detailed map of the part of the body where the tumor is located. And this is, creating this map is what is called segmentation within this context. And to create this kind of segmentation map is a very tedious and time-consuming task. For example, if someone has a head-neck tumor, it takes doctors between 4 and 6 hours on average to do. And if someone has a brain tumor, it takes on average 1 hour to segment. And we can think about if we were to scale up radiation treatment to 50% of all cancer cases in the world, and we do a back-of-the-envelope calculation on that, we reach the conclusion that we would need around 10,000 doctors working full-time only doing segmentation. So this is the first thing that we want to help with this project, to see if we can use machine learning to reduce the time that doctors need to spend on this. Another problem of having humans doing this segmentation is that the final quality of the segmentation is very dependent on the skill of the doctor. So one study showed that if you take two doctors and look at their segmentations, they will have a similarity score of, on average, 85%, where similarity score is measured using F1 score. And this, to me at least, seems a little bit worrying, right? 85%. And that is the second thing that we want to help with, to be able to take the skills of these more experienced doctors and transfer it to the less experienced ones. Right. So let's dive into the data set that we've been using and define our problem a little bit more in detail. So we've been using this open source data set that comes with the multimodal brain tumor segmentation challenge. And this data set is a standard data set for benchmarking these kind of algorithms. It consists out of 276 patients that all have brain tumor. For each patient, we have 4 different kinds of 3D MRI scans. And we also have a ground truth segmentation. And the segmentation has 4 different tumor classes. So what we want to create is some kind of model that takes these MRI scans and outputs the segmentation map, right? And already here we are starting to ask questions, right? We only have 276 examples. Will that ever be enough to create some useful model? But we'll try and we'll see where we end up. So let's start to dive into the specific models that we've been using. So we use deep neural networks for this. The thing that is nice with using those is that you don't have to do much feature engineering yourself most often. And you can usually feed the almost raw data into the network. The network will learn good representations. And I'll try to give you some intuition around the specific model architecture that we've been using. And to give you that, we'll start by looking at a very classical architecture for unsupervised learning called the autoencoder. So the autoencoder can be decomposed to consist out of 2 parts. First an encoder, then a decoder. So what we do is that we take the input, feeding it through the encoder, end up with some kind of encoded representation, which is then fed to the decoder, and the decoder then outputs some new image. We then train this whole architecture to minimize the difference between the output image and the input image, right? But then the question is, why would we like to create this kind of very complicated copying machine? So here in the middle, we have a bottleneck layer, which contains much fewer neurons than the number of pixels in the input image. This forces the encoder to compress the input image and create some more high-level representation. And then the decoder will also have to learn how to decompress this high-level representation into something that looks like the input image. So starting here, we could think about ways to change this into something that could do segmentation. And the first naive approach would be to just switch what the output target is from trying to recreate the input image into trying to create this segmentation map, right? But when I try to train this, it doesn't work at all. Like, you get 0 score. And some researchers from University of Freiburg with Olaf Ronneberger in the front, now at DeepMind, I think. He came up with this architecture called the UNet a couple of years ago, where you have an autoencoder structure as the base, but you also add some skip connections to it. So the input now can flow both through the autoencoder, but it can also skip some layers. And by doing something like this, you give the opportunity to the decoder to not only use this very high-level representation to create the segmentation, but also to be able to use more low-level representations. And this architecture has been used a lot for segmentation, and especially within the biological image domain. Looking a little bit more in detail what the layers of this consist of, we first have some convolutional layers, then we have an optional regularization layer, either dropout or batch norm. We then have some nonlinearity, and then finally a pooling layer. And this is for the encoder part. For the decoder part, it basically looks the same, but we also have, or instead of a pooling layer, we have an upsampling layer. So how did it go when we tried to train this? Well, we instantly get 97.6% pixel level accuracy. So great, right? But then when we look at the qualitative results, we actually see that our networks didn't learn anything. So here the first 4 columns are the input, then we have the target, then finally we have the predictions. So network predicted that we don't have any tumors anywhere. So this is catastrophe, right? We wouldn't be able to deploy this anywhere. And then the question is, why is this, and how is it disconnected to the fact that we were almost 100% correct on a pixel level accuracy? Well, if we look more in detail at the data, we see that we have a massive class imbalance, where we actually have 97.6%, the exact same number as before, being non-tumor pixels, and only 2.4% of pixels being tumor pixels. So here we see that it's obvious that the network could be almost 100% correct by predicting that there are no tumors at any time, right? But not so good. So how do we mitigate this problem? Well, we change what the network focuses at, or what the training focuses at. So in the first attempt, all errors were equally bad, right? It was equally bad to be wrong on a tumor pixel as on a non-tumor pixel. But now we change this and say that it's much worse to be wrong on a tumor pixel than on a non-tumor pixel. And we do that by changing the loss function that the neural network is trying to optimize. Changing it from a categorical cross-entropy to a weighted categorical cross-entropy, where the weights for each pixel is 1 divided by the square root of the class frequency for that certain pixel. And this means that for classes that are very uncommon, like the tumor pixels, the weights will be much larger, while for the common class, the non-tumor one, the weight will be much smaller, right? And when we train the network using this loss, we instantly get much, much better results. Now the predictions look qualitatively quite similar to the actual targets. And but it's still not perfect in any way, because we changed the weighting to something that is slightly artificial. We now get over-segmentation. This means that the network tend to predict slightly larger tumors than there actually are. And this gives rise to the question of if there are errors that are worse to have than others. For example, is it better to be on the safe side and segment a little bit larger than the tumor actually is? And this is somewhere where we, of course, need to collaborate more with domain experts to take it forward. But if we then look at some quantitative results and compare how well doctors are doing compared to our algorithm, we get this. Here, the first column is the score of doctors. These numbers are from a paper that comes with this data set. And the second column is the results of our network. The numbers here are also F1 score. The rows here are different parts of the tumor. So the first column is the whole tumor. Then we have the core part of the tumor. Then the third row is the part of the tumor that is still growing. And we see that for the first 2 rows, we have almost the same results for our network as for that doctors have, while for the third row it's lagging behind a little bit. And we got our results by uploading our segmentations on the test dataset to an online evaluation tool. So we had never seen the ground truth for this ourselves before. And we have to remember that these results come from training on only 276 images or data points. And the question is then, how come? How is it possible to get this good results with these few number of data points? And one hypothesis is that how much data you need is very domain dependent. So here I plotted a bunch of random examples from 2 datasets. The first one being the tumor dataset, and the second one is the ImageNet dataset. And if we start by looking at the tumor dataset, we see that the data points here are structurally all very similar. So we could imagine that to be able to cover a large part of the possible variation within this domain, we might not need that much data. While for the ImageNet dataset, all data points look very different. And we can imagine that to be able to cover a large part of the variation within possible natural images, we would actually need quite a lot more data points. And this is something that I want you to take with you when you go back to your companies and are asking yourself the question, how many data points do I need to build some model? Well, the question that you might ask yourself instead is do we have enough data to cover a large part of the possible variation within this domain that we are trying to solve a problem in? Right, so let's continue into some practical details of this project. So we trained around 100 different neural networks. They took at most around 20 hours to train, usually much less. We could usually stop them or sometimes stop them if we saw that the training wasn't going very well. The whole project consists out of around 1,000 lines of code, where only 20 lines of code are for defining the neural networks. And these numbers are very much in line with a paper that was released by Google a couple of years ago called The Hidden Technical Depth of Machine Learning Systems, where they report that they've seen that usually 95% of the code in these kind of projects are glue code and only 5% are machine learning code or model building code. We built all of this in Python using TensorFlow and Keras, using TensorBoard extensively for monitoring results. All of the models were trained on an in-house desktop with 4 12GB Titan X GPUs, 256 gigabytes of RAM, and 40 CPU cores. And the cost of a computer like this is around 100,000 Swedish crowns, 12,000 US dollars, if that's a reference. But we would definitely be able to train it on something much cheaper. One of my colleagues bought a desktop computer a couple of weeks ago for around 15,000 Swedish crowns, and we would be able to train the models on that one. I also want to briefly mention a few challenges that we faced during this project. First one being reproducibility. So you run some model today, and then you come back in a couple of months, and you want to recreate this model or the results for some reason. And one reason why this can be challenging is that we're using a lot of open source tools, and they tend to move quite fast. And from time to time, you have breaking changes. Also, in the neural network libraries that we're using, they're also still quite immature. Another thing that is kind of surprising, that is still quite challenging, is bookkeeping of results and configurations. Like what the configuration led to what results, how the different parameter settings affect the result. Also versioning control of models, of data sets, code and configurations, results. All of those are still a little bit of a challenge, and the tooling around this is still quite immature. But I believe that we'll see a lot of things happening in this space within the upcoming time, and this is also something that we at Peltarion want to help with. Then finally, some words on future work. So as we saw, the data set that we used in this project was quite small, and this is unfortunately very often the case within within the medical field. And mainly for the reason that, that of privacy concerns. It's difficult to get hold of data sets, but also due to that labeled data within this field is very expensive. On the other hand, you have a much larger body of unlabeled data. So what we want to do as the next step in this project is to be able to combine unlabeled data with labeled data and do what is called semi-supervised learning. And earlier this year, there was an interesting paper released by Sole et al. From University of Central Florida, where they used generative adversarial networks to do semi-supervised segmentation. And I also know that the next speaker is an expert in semi-supervised learning, so I'm very much looking forward to that presentation. And with that, I'd like to conclude my presentation. Thank you all for listening.